Good morning, guys. In the last lecture, we started the magnetic material part. So, basically, we saw the origin of the magnetism, which had three parts: the nuclear part, the electronic part, which had two part again, orbital part, and the spin part. Okay, but nuclei is heavy compared to the electrons, so we finally said that we're going to consider only the electronic contribution while calculating the magnetic moment mu. And magnetic moment will in general will calculate in the units of Bohr magnetron, mu b. Okay, we also defined something called magnetizing field, the external applied magnetic field. And because of this magnetizing field, which is the cause, we had the magnetization, which is the effect. Okay, which is also, let's say, magnetic dipole moment per unit volume. And finally, we also defined the B, which is magnetic flux density or the magnetic induction. Okay, so now I'll define the remaining few more quantities similar to the dielectric part. So first one is in the dielectric part, recall we had a relation D is equal to epsilon naught E plus P. So D is called the dielectric displacement. The first one is the external, the electric part. The P is the polarization. So similarly, in the magnetic field case, we will denote something like the magnetic induction. I'll denote it like B int, which will have two parts. One is mu naught H plus the second is mu naught M. So first one is again the external applied magnetizing field H, and the second part is the let's say the internal contribution. And what do I mean by internal contribution? It means because of the external magnetic field, we have the magnetization which gets generated in the magnetic material. All right, so that's why it's the sum of these two. Okay, and just to distinguish, because last time you had some confusion, so I'm denoting this int, which is clearly telling you that it's the magnetic induction created inside the material. Okay, so I'll just write it down. So it's magnetic induction created inside the material. Okay, so here the mu naught is called the magnetic permeability of free space. The naught is, or you can say 0, it's denoting the free space part, the vacuum thing, like the last time. So I'll write it down, magnetic permeability of the free space. And its value is 4 pi times 10 to the power minus 7 Weber per ampere meter. So you can calculate its unit because you know the unit of magnetic induction B, which is Weber per meter square, and you know the unit of magnetizing field, which is ampere per meter. So from here you can calculate it's Weber per ampere meter, or we can say it Henry per meter also. Henry per meter. Okay, and just to distinguish, mu we also used for magnetic moment. Okay, so mu we used for magnetic moment, mu naught or mu 0 we are using for the magnetic permeability for free space, and mu b, capital B, we are saying it Bohr magnetron. So three kind of mu's have been introduced in this section. Okay, so now imagine if there is vacuum, so in vacuum, meaning there is no material inside, just the free space, there is no material. So the magnetization created inside the current carrying coil. You remember I also drew a current carrying coil, something like this. Let's say I. So inside, for example, in this yellow space, there is no material in vacuum, meaning no material. So in this case, the if there is no material, so the magnetization will be zero, right? So the mu naught m part will be zero. So hence the B internal will be equal to mu naught H, meaning whatever you apply externally, that's going to be your internal magnetic induction. Okay, so I can also say, let's say this thing is our B naught because it's for the free space. That's why we can just ignore the int, the subscript int. And now instead of, let's say, the instead of vacuum, if we have some material there, so this B int will be the sum of both mu naught H plus mu naught M, or in some sense I can just write it down, B int is equal to B naught plus mu naught M. Okay, in general, with some material. So generally, let's say, for example, if you put copper or aluminum or silver or superconductor or iron inside the solenoid, meaning this yellow part will be replaced by any of these atoms, so then the magnetic ability to look into this material so will be different, meaning the magnetic flux lines which will pass through these material, whether it will pass through or not, and if it passes through, how much it will be, it will depend, it will vary from material to material. So let me draw a diagram or a plot between the induction, inductance I can say, and the magnetizing field. So for example, when there is vacuum, so we know, let's say this is B, this is H, okay? So when there is vacuum, we know that B is equal to mu naught H. So this is going to be a linear plot. Sorry. So it's this, and it's vacuum, B is equal to mu naught H. And if you want to see how in the coil, I mean what's going to be the physical system, it will be something like this. Just the coil will be there, so current I, okay, and the magnetic field will be B is equal to mu naught H because of this current carrying wire. Okay, now in the presence of some material inside, the slope will change. So the slope will become, let's say, B is equal to B naught or plus mu naught M, meaning this difference will be mu naught M, right? Because B naught is equal to mu naught H. So this is the case when there is material inside. And if the physical system will look something like this for this case, but this time there's gonna be a material. This red patch is the some material inside. So then there is, let's say, this H, and B is equal to B naught plus mu naught M. Okay, and here the I. Okay, I can just shift this thing. That's okay. All right, so this is the how a current carrying coil generates a magnetic flux inside a magnetic material, and what's going to be the figure between the inductance and the magnetizing field. All right, so in general, so depending upon this red patch, which is what kind of material inside, the magnetic properties can be different. Okay, so for example, if you put a superconductor, you know the superconductor, right, which have almost zero resistance once we decrease the temperature below a critical temperature. So in case of a superconductor, the flux density or the induction inside is actually zero, meaning the all the field lines, the material repel them and throws them outside, meaning the B int is equal to 0 inside the superconductor, which means this implies that B naught has to equal to minus mu naught m, meaning whatever magnetic field you apply, magnetizing field B naught, the the magnetization inside the superconductor, it just cancels it out. That's why inside there is no magnetic induction at all. So the entire magnetic flux is excluded from the inside of the superconductor in the superconducting state. So I'll just write it down. It's a really important feature of a superconductor. So entire magnetic flux is excluded from inside the superconductor. Let's say instead of superconductor, if we have silver, the material is silver. Then what happens? So for silver, and okay, so all these things I'm telling, so you can think it's you have some supernatural power to see through those material, meaning what the field lines are doing, meaning they are getting excluded or they are concentrated in the material. So it's kind of a thought experiment, okay, but experimentally clearly we have seen all these features. So once, let's say the material that you're using is silver, so then what happens, the B naught, the beant, the internal inductance inside the material is smaller than B naught. It's slightly less than the externally applied field, which means that the sum of the flux is excluded from inside of the material. Sum of the flux gets excluded from inside the material. All right, so these kind of material where the internal magnetization is smaller than the external one, those materials are called diamagnetic materials. So till you remember in the previous lecture we saw 4 type of magnets: paramagnet, ferromagnet, antiferromagnet and ferrimagnet. So there is one more class, so total there are 5. So these kind of materials, they are called, these kind of materials are called diamagnetic material. Uh, so to specifically saying, whoever excludes the field from inside the material, it's diamagnetic. But as you can see in a superconductor, it excludes the entire magnetic flux. So that's why these superconductors are really special because they are perfect diamagnetic materials. Okay. All right, so apart from that, let's say for example, if you put copper or aluminum, the third example, if you put copper or aluminum uh, in the solenoid, so then what happens? This B internal, it's greater than B0. So it's slightly greater than the external magnetizing field. So these kind of material are called paramagnetic material, meaning the flux lines will be slightly concentrated inside the material. So flux lines concentrated inside the material. And these are called paramagnetic materials. Okay, so there are also, let's say, instead of copper, aluminum, if you put iron, so these are called ferromagnetic or ferrimagnetic material because the flux lines are heavily concentrated. So if you put, let's say, iron, so then the B int would be significantly higher than B naught. Okay, so these are ferromagnetic or ferrimagnetic. Okay, so these are the so later you will see we'll discuss different all these different class of these 5 classes in a bit of great detail as we go along. But before that, let me introduce 2 more quantities similar to the dielectric one. So these are I think the final 2 quantities, let's say. So one is the magnetic susceptibility, so which we denote by chi m. So remember there it was chi e, the electric susceptibility, and I'll also, let's say, give a precise definition of magnetic permeability, which will denote as mu. Yeah, it can be a bit confusing because we are calling permeability also mu and magnetic moment also mu, but I'll say that magnetic moment will generally denote in units of mu b Bohr magnetron, so you'll be able to distinguish it. Or I'll make this statement more specific depending upon what symbol we are using where. So the magnetic susceptibility, first, how chi m is defined? Chi m is defined as the a property which relates the magnetization and the magnetizing field, and basically it's a ratio between m and h. So a property that relates m and h, effect and cause. And for example, for diamagnetic and paramagnetic material, the B int, the internal inductance or the internal flux density, it is generally linearly proportional to the magnetizing field, meaning I can write B int is equal to mu h. Okay, so this mu here is called the magnetic permeability of the mu is equal to magnetic permeability. See, only for dielectric and paramagnetic, the B int is linearly proportional. Okay, for others, depending upon the system, it can be different also. So that's why I'll write for diamagnetic and paramagnetic. Okay, So the quantity which relates B int and H, it's magnetic permeability, but we also know that B int is equal to B naught plus mu naught M, right? B int, and this is equal to mu H. So then we can write it down that B int, I can say that it's equal to mu naught mu R H, which is same as mu naught H plus mu naught M. So I just expanded B naught as mu naught H, and in the mu we are going to define the similar fashion. Like there we had relative permeability, here we will be having relative permeability mu R. So mu R is called the relative permeability, and we are going to establish a relation between the chi m and this mu R. So from here, if we will solve it, we can get that m is equal to mu R minus 1 H, right? So magnetization in terms of mu R. So this relation gives us it relates the relative permeability and the cause and the effect. But let's say we had chi m is equal to m divided by H. So this implies that chi m will be mu R minus 1. So this is the final expression that I was looking for. Uh, it relates the permeability to susceptibility. Okay, or we can also write this is same as mu R is equal to 1 plus chi m, as we wrote for the dielectric case, epsilon R is equal to 1 plus chi e. So if you want to understand what susceptibility physically means, so susceptibility actually represents the tendency of a magnetic material to fall for the presence of magnetizing field. Okay, so that's what the susceptibility actually tells us. So now we have, I think I have introduced all those quantities which we also saw on the same footing for the dielectric material, but this time for a magnetic system, and we also related the permeability and susceptibility in the same fashion. The next topic that I want to discuss is it's called demagnetizing field. So let me write it down first and then I'll discuss what it is. So demagnetizing field, as its name indicates, it demagnetizes. Okay, so for example for a diamagnetic and paramagnetic material, the magnetizing field, remember we were saying that we were not differentiating between the inside field of a paramagnetic or dielectric material and the applied field, the capital the capital H, the applied magnetizing field. But what happens when we have, let's say, ferromagnetic or ferrimagnetic material? So the field inside the material, I can denote it, let's say, H int, it's actually different than the applied H. Why? Because these materials, they exhibit large magnetization M. So that's why the let's say the magnetic field inside, it's different than the one that you apply. And what demagnetizing field does, it basically causes the magnetic flux lines inside the magnetic material to move in a direction opposite to the one that you apply. All right, so I can just write it down let's say the magnetizing field inside the ferromagnetic or ferrimagnetic is different than the uh, magnetizing field. So magnetizing field, which was the external one, H end, and the magnetizing field inside, we will denote as using H int. Okay, and the reason why it's different, why? Because the M is pretty large for these kind of materials. So sorry, so because of this thing, so now if you ask me to write down, let's say the B int, so you remember in the last section, B int we wrote mu naught H plus mu naught M, last section, let's say. But now because of this demagnetizing field, the B int, it becomes mu naught H is fine, plus there will be mu naught 1 minus nd times m. So this ndm, this is the, one can say that it's HD, demagnetizing field. All right, so so this ndm in the above equation, it decreases the magnetic induction by partially neutralizing the external force H for the magnetization M. All right, so and this, the Nd is called demagnetizing factor, and this demagnetizing factor, it depends upon the geometry of the material. It depends on, and it depends on the geometry of the sample or of the magnetic material. And it varies from 0 to 1. So depending upon if the material is in toroid, cylindrical shape, sphere, it can change. Okay, so this is what is a demagnetizing field, which basically, because of the magnetization, the material inside feels some different magnetic field, H int, rather than just the H. So that's what is the demagnetizing field is, and it is, one can quantify it using a factor which is Nd, which is from 0 to 1, depending upon whether the demagnetizing field has completely overtaken, or you can see from here, right, if Nd is equal to 1, then the M part will be completely gone from this equation, and Nd will be 0, then there is no demagnetizing field at all. So that is, so depending upon that, you can tell how much field the ferromagnetic or ferrimagnetic material is feeling inside its system. Okay, so this was demagnetizing field. Apart from that, now I want to introduce the classification of magnetic materials. So I think I have introduced all the all the definitions and parameters that I need to discuss. But just to give you a quick recap, till now we have seen 5 types of magnetic material. So in the beginning, I just told you about the 4: paramagnetic, ferromagnetic, ferrimagnetic, and antiferromagnetic. But then we also saw there is something called diamagnetic materials, where the magnetic field lines gets thrown out of the sample by some amount. If it's completely thrown away, or the system repels the magnetic field lines, then it's a superconductor, perfect diamagnetic. Otherwise, there are plenty of other materials um, uh, which falls into this category. But now there is um, some other ways also to describe magnetic material using, let's say, magnetic susceptibility, a relative sign of these values. Let's see a bit more detail the classification of the magnetic materials. So, classification of the magnetic material. Okay, so first we'll discuss diamagnetic material. So in diamagnetic material, what happens? You apply an external magnetic field, and the material tries to exclude the magnetic flux. So when an external magnetic field, I'll just say external, okay, let me just write it. Magnetic field is applied, the material excludes the magnetic flux. So this is what the diamagnetic property is. Okay, so the examples are metals, inert gases, and organic compounds. Okay, so diamagnetism, it's basically it's the property which comes from the orbital motion of individual electron in the presence of field. And you can think of that, see, I'm saying that the material, it expels the flux line, so one can think of why this thing is happening. So it's actually like the Lange's law, if you remember. So in Lange's law, basically what happens that the back EMF of the induced field, it opposes the changing current, right? The effect is actually opposing the cause. So it's in the similar way. So you apply a magnetic field, and the material inside, it opposes whatever you are applying. It doesn't want to change its condition. So in some sense, it's like that. So I can just start it that diamagnetism, meaning it comes from orbital motion of the electron. The another characteristic of diamagnetic materials are the relative diamagnetic permeability, which we had denoted using mu r, So this is, it's less than 1. So if mu r is less than 1, this implies that the chi m would be negative. Remember, chi m was mu r minus 1. So that's why the magnetic susceptibility would be negative for diamagnetic material. One can also note that the atoms in the diamagnetic material, they do not have a net dipole moment under if you do not have any magnetizing field, meaning that once you apply the magnetizing field, the magnetic moment gets generated at an atomic level. Okay, so if let's say we have even numbers of electrons, so there won't be any net magnetic moment. The net magnetic moment at the atomic scale would be 0 for each atom. So then the applied magnetic field, it distorts the electron's orbital motion, which leads to the diamagnetic kind of behavior. All right, and we know that the magnetic moment in a diamagnetic material, it comes from the precessing motion of the electron, meaning not the spin part, it's basically the orbital part. So the one can also think of that in the sense of temperature, that the diamagnetic susceptibility, it's independent of the temperature. This is highly contrast with other kind of magnetic behavior materials where it depends on the temperature. So I can start this thing also down, that susceptibility. So this is also one of the characteristic of diamagnetic material, is independent of temperature. Okay. So as I said, that the tendency of diamagnetic material is to expel the magnetic flux lines out from its interior. So the perfect diamagnetic, I have told you before also, it's superconductor. So just to give you an idea of superconductor, so what happens in a superconductor? So basically, when the temperature T, it's smaller than the critical temperature. Okay, so there, here also one can be confused in the sense that critical temperature also we denote using Tc, and Curie temperature also we denote using Tc. Okay, so both, but whenever we talk about superconductor, it's always the critical temperature. So what happens? So below critical temperature, let's say Tc, uh, the resistance basically goes to 0, and your system is called that the system has gone to a superconducting state. Okay, and just to contrast, I'll just write down in the bracket that we have also denoted, or we will also denote, even here we have Curie temperature, like the dielectric one, Tc. So you see that this C here is Curie, that C there is critical, but yeah, I understand. But I'll be specific what which temperature or we are discussing. So the this is another, let's say I'll just write down perfect diamagnetic material. Okay, it's a superconducting state. So for a superconductor, the chi m, it's equal to actually -1. All right. So as I said, the for diamagnetic materials, the susceptibility would be negative. So there is a really important difference between a conductor and superconductor in terms of how they react to the magnetic flux lines. So this effect is also known as the Meissner effect. So the expulsion of magnetic field lines due to uh, diamagnetic behavior. So something called Meissner effect, which is expulsion of magnetic flux lines due to diamagnetic behavior of a superconductor. And this expulsion of the magnetic field lines, it's the basis of the magnetic levitation using superconductors. This you might have done an experiment, or you might have seen it in some videos or somewhere. Okay, so what is it? So the if you bring a permanent magnet close to a superconductor, it tries to expel the magnetic field, and the result is the magnet can float and levitate over the superconductor. Okay, that's basically the magnetic levitation. So how the I mean, what do you see experimentally when I say expulsion of magnetic field lines, and the difference, major difference between a superconductor and a conductor? So let's say this is our, sorry, this is our sample. Okay, this thing over here, I need different color. So so let's say this yellow thing is our sample, and we apply the magnetic field lines. It's like this, passing through the sample B. Okay, so if, let's say, this is the case when T is greater than Tc, meaning things are normal, whether we are talking about a superconductor or a normal perfect conductor. So when the Tc is smaller than T is smaller than Tc, then what happens? These magnetic the flux lines, they get excluded, so the sample doesn't like them. So field lines behave something like this. So this is again the direction of P, and this is our superconductor. All right. So below Tc, it expels all the magnetic field lines from inside to outside. It doesn't like that. But what happens, let's say instead of a superconductor, you had a conductor. So when T is greater than Tc, things are same. So there will be, this is, let's say, our B, and superconductor I just denoted using green. Now this is T greater than Tc. Okay, so what happens when T is less than Tc? Then it remains same, meaning this is conductor, perfect conductor. Okay, so here is the major difference between a superconductor and a conductor, meaning superconductor, it expels the magnetic field lines from inside to outside, but for a conductor, basically it's the same thing, whether it's T greater than Tc or T smaller than Tc. Okay, so this happens, as I said, we cool down the sample, right? Here T was greater than Tc, then we went to T smaller than Tc. Here also the same, we cool down it. So the perfect conductor, it continues, the magnetic field lines continue to penetrate the sample. However, superconductor, that's not the case. Okay, so this was the diamagnetic from the more susceptibility and permeability point of view. The next one is the second type of materials are the paramagnetic materials. So in the paramagnetic materials, when you place a paramagnetic material inside the coil, the flux density inside is slightly larger than the B naught. B naught was, you remember, mu naught H. So the main origin of paramagnetism is because of the unpaired electrons in an atom or in an ion. So this leads to a net magnetic moment of a free atom or an ion. Okay, so I'll just write it down. So paramagnetic material effects originates from the unpaired electrons. And this leads to a net magnetic moment. For the atom or ion, whichever we are discussing. Okay, so the atom or ion is known as, let's say, paramagnetic atom or a paramagnetic ion. The example I have given before also, aluminum. So the atom in these material, they have a permanent magnetic moment because of the unpaired electron. And when you apply a magnetic field, these magnetic movement, they get oriented um, in the same direction as the applied field and create a magnetization. Okay, so um, in the paramagnetic material, the susceptibility is very small, but it's positive. Susceptibility is very small. Just to give you an estimate, it will be of the order of 10 to the power minus 3 to 10 to the power minus 6. Really small, but it is positive, not like the diamagnetic one, which was negative. And it depends on temperature, because if the thermal motion becomes relevant, then even though the individual atom or ion will have a magnetic moment, the overall effect would be something else compared to um, the one that we had before. And actually the susceptibility, it decreases because of the as you increase the temperature. So I'll write this one also down as T increases, the susceptibility chi m decreases. Okay, you might have seen an experiment of liquid oxygen when liquid oxygen is deflated by strong permanent magnet. I am not sure about that, whether you have seen it or not. So actually, there is an absorption of red light and it impart a blue color on liquid oxygen. So this happens because of the unpaired electron that create the magnetic moment in the oxygen, which is responsible for the absorption of the red light. But nonetheless, the paramagnetic material, they get slightly attracted in the presence of a permanent magnet, not like the diamagnetic one, which generally repel the not generally which repel the field lines. So I will start it down also. So paramagnetic material show slight attraction in the presence of permanent magnet. Okay, but the paramagnetic response is really small. You can see the susceptibility is pretty small, of the order of 10 to the power minus 3 or at the most. So the main you can say the effect, it's hardly visible. So most of the material, they are considered, if they are paramagnetic, they are considered as non-magnetic. And another important point is that at Curie temperature, the ferromagnetic or ferrimagnetic material will transform into the paramagnetic material. Like the dielectric case, there were ferroelectric material which were transforming to paraelectric material once you cross the Curie temperature. Okay, so I'll write it down also. So at Curie temperature, ferromagnetic material transform into, you go from, let's say, ferromagnetic material to paramagnetic material. And here Curie temperature is again Tc. Okay, all right. So this is so till now we have studied only two of them, paramagnetic and diamagnetic material. In the next lecture, we'll see the ferromagnetic and the anti-ferromagnetic materials as well, and we'll see the hysteresis curve in a similar fashion like the dielectric one for the magnetic materials.